Hail there, fearless ranger. Do you want to join our quest for glory? Then welcome aboard, my friend. Together, we shall unravel the secrets of this Biome Core graph.
It's time to learn the foundation of all this, the Biome Core graph, the very brain of our operation. It's where all of the processing is done. Let's take a quick peek under the hood here. Let's start with the simplest one, the biome cache. We've seen it so far on our Biome Core. If we click the debug biome cache, this is the biome cache.
Oh no, it's ugly!
No, your mother. Let's use the sample level. This one is a bit more complex, and turning it on. So this is the biome cache. This here does the calculation for our biome cache, and it's computed from all the biome actors like the volume and the spline we used earlier, and the texture projection which we will use later. This tiny thing here is our debugging for the biome cache. After the biome cache, this here is for our generators. Our biome assets use a generator graph to create the root points. These root points are bound to a biome that they belong to. And if we open one of our generators, let's see here, the bounding shape of our surface sampler here is filtered by the biome cache. With the generator done comes the next part, where the biomes are applied. So after the root points are generated, the biome cache applies which biome it belongs to and then assigns a biome asset to it. All the biome assets and their parameters are then stored in this root asset table. With that done, next the priority is sorted out, like which generator has higher priority when two of them are overlapping. After that are our filters. There is a global parameter here that lets you bypass all these filters. And the filter can be anything from a density or a position based filtering to using a texture to filter the points. It can be as simple as you want or as complex as you can make it. And each biome asset controls that filtering behavior for each of the entry in the biome asset array. So similar assets can have completely different behavior based on the filtering. And if you are smart about it, then you can even lower the number of biomes that you have to use. In conclusion, filters are fantastic. Just remember to pray to the filter gods before you use them. Moving on, recursion and transform graphs. So when a root point is spawned, we take the position of that root point and then we transform that position by duplicating it around a bunch of times and using that to spawn a child asset. This one here uses a recursion graph, meaning let's take a root point, say a tree. Now that tree can have a child, let's say a leaf pile. The leaf piles are then spawned based on a transform graph and scattered along that tree. Now that leaf pile can further have a child, let's say a single leaf, then you can scatter that around those leaf piles. And this can go on and on, as many children as you want. That's why it's called recursion. And it's controlled by a global parameter, the max child asset depth. If it's set to 1, then it will only allow one child. If it's set to 2, then it will allow 2 generations of children. And so on. A very effective family planner indeed. And just like our root points, the child points can have their own filters. Doesn't need to be anything complex because you already control the complex part for the root points. After the transforms, we spawn our mesh or a PCG data asset or any other actor. There is also an output. We put different stuff here and it's controlled with a global parameter called here, the output data for runtime generation. As the name suggests, the data that we plug in here we will use a get PCG component and use that in our runtime graph. Other than that, there is the stuff that we skipped, this blue part. This is to introduce some external data in your graph, and we will cover it in the artistic control episode. For now, we have a general idea of how the graph flows. Do you know what else flows? Yeah, what? My tears when I see this graph. Hey. Let's do a deep dive of the components of this graph. But before we do that, sip on your espresso. It's going to be a long ride ahead. And let's start with the first one, our biome cache. By now you are already quite familiar with the biome cache. With the biome definition, we define our biomes. Here the biomes are already defined, some with textures, some with volumes and splines. So the biome cache is a way to store the biome data in a 3D grid, which separates each of the unique biomes. And later we use it to identify those biomes. As you can see, it's a 3D structure. That means it has verticality. I think I might have already given an idea of what that means. Let me explain regardless. Say you have a forest, like right here. You can have a floating sky island on top, and you can have a cave system down there. Let's actually add those to paint a picture. I'll bring in a cube. My thumb is bigger than that cube. And by thumb, I mean my finger. Let's make it 100 by 100. Still bigger. That should be good enough. Right. So this is our forest. And let's use a biome volume right here. And give it a biome definition. Let's use this one. I think it's coniferous forest. We assigned a definition to this volume. It also needs a biome asset. Since we've already assigned an asset to the coniferous forest there, we don't need to assign it again. We only need to define it once, and we have already defined it using a blueprint that we call biome setup. Why is it not showing up then? Patience, my child. Interesting. Let's go to the biome asset in the generator. So the generator only uses the landscape data, but we are telling it to spawn on a mesh. So instead we'll use word ray hit query. It should have showed up. Let's refresh it. Could it be a bounce issue? Let me grab that. That worked. Let's delete all these. And it's showing us that coniferous forest. And similarly, we can just, let me delete this. We can just duplicate this, maybe not that thick, and put it way down here. And again have a biome volume, and this time let's say desert. Let's find the biome asset, and instead of this, let's use a generator which has the word ray hit query. And just as it happened with the other one, it's going out of bounds. I'll show you out of bounds. So let's change the volume Z to say 600. That should be in the bounds. So to refresh, let's change it to a different one and back again. Here the biome showed up. And again, the biome cache is 3-dimensional, so you can have as many of these biomes in 3D space as you want. 2D is still possible. If we go to the Biome Core, there is a global parameter, the biome cache cell size. If you change the Z to a higher value, let's say 6000, still not enough. maybe 100,000. Yeah, so in that case the verticality doesn't mean anything and it's a 2D grid essentially. Let's set it back to a lower value. Each of these small cells in the biome cache can only hold a single biome, or I should say a single color. Like the red here represents the desert biome. And if there are two biomes overlapping, then it will take the one with the higher priority. By lowering the cell size, we can increase the resolution, let's say 200. So the lower the cell size is, the more precise that overlapping between biomes would be. Probably not that scientific, but here's a side by side to compare the cell sizes and how it affects the blending. And the color, priority, and the name, all of that is defined in the biome definition dataset that we already covered in the first part. But how do we use those biome definitions to define our biomes in the biome cache? We've already used spline or a volume to define our biomes, and there's another way to define them using a texture projection. If we go to our graph parameters, there is a texture projection that we use to project a texture on our landscape. With that, the biome cache is good to go. So with the biome cache generated, since we use it as a bounding shape in our generators, we take the biome asset from the root asset table and match them to the points generated with the generator graphs. That should be enough about the biome cache. So let's move on to generators. They generate the root points. Let's open a generator. It's a logic to create the root points. You create your own logic and then export some parameters and then control them later using a PCG graph instance. Then we use that graph in our biome generator dataset. That dataset needs a generator type, a priority, and a generator graph. Generator is nothing but a logic that you customize based on your needs to spawn the original points, also known as the root points. And then we can use a PCG graph instance of that logic to easily customize without needing to build custom logics over and over. The generator priority sorts between the generators, and there is a boolean, this generator allow overlap, that we can use to switch whether we want the overlap or not. That would be helpful in cases such as when you want to spawn ground assemblies. They can easily overlap with other assets, and switching on the boolean would mean other assets can spawn over that ground assembly. Back to our Biome Core graph. After the points are generated with the generator graph, we assign them to a biome and the biome asset that they belong to. After all that, we apply the priority based difference. Why does it matter that we do it after? Because instead of, let's go to the desert biome asset and debug the bounds. Since that root point now has a biome asset, that means the bounds are based on the mesh it belongs to. Meaning when we are deciding the generator priorities, the bounds are already generated based on the thing it's spawning. So it considers those bounds when we are doing this difference operation here. Each biome asset needs to have a generator, because without the generator there won't be any points to assign this mesh to. Let's actually debug this difference here so we can see what it's doing. Let's do this tree maybe. It should be the broadleaf biome asset. Let's open it. And we got our tree number 1 from the bounds and this tree number 2. Let's click show bounds. They are using the same generator, which is the shared trees. Let's use another one maybe. All of them are using shared trees. Let's change it to shared rocks. This is a bad example. It's really hard to see. Let's try maybe the desert instead. Yeah, this should be good. Let's delete all the other ones. Our first generator here has a priority of 0 and let's say 1 for the other one. Let's actually do 0 for this one and maybe 3 for the other one. We are using shared rocks and the biome tutorial generator here and here. Let's also allow overlap for our rocks. The rocks have way too low density, so let's increase it to maybe 1. And this one to 200. So they can at least overlap. Maybe 2 and 100. And let's do the same with our biome tutorial generator. And maybe 1 and 2 and 100. The children are annoying, so let's also turn them off. Wish there was a button for that in real life. Let's also get rid of the filters. Oh, that is too much. But hopefully you get the point, if we can even see that. So these boulders overlapping with the cactus, if we say we don't want any overlap, and since the rock has a higher priority, all the places where the rock and the cactus were overlapping, the cactus was removed. And if you do it the other way around, let's change the priority, higher than 3, so 6. This time all the rock is removed where they are overlapping, which is pretty much everywhere. Let's put it back to 0. Now the rock has a higher priority. Which brings us to the next part. Filters. Ah yes, the only thing standing between my selfie and a horror movie. But we all know it's the inside that matters. Continuing on. In our Biome Core graph there is a global parameter that takes the filter graph. Let's open it. It's a PCG graph instance with a bunch of parameters that we can override. So it's using a density filter and a flow projection. These are the texture based projection and a distance based filter. You can add more filters to the graph. This graph here is a filter for our root points here, and the filter for the children is later after they are spawned, which is controlled by a similar graph. If you can control the root points, then you don't need the same filters for the children, since they have no chance to spawn unless a parent is nearby. It will spawn if there is enough distance in the transform graph to allow it, but it's a case by case basis. So if you want a better control over your children, then you use extra filters for the children. Let's go through the main graph, the root point filters. So the density filter, the first one, it's really straightforward. You might even have used this in your PCG graph. It's just a simple attribute noise. Then we have these two that are texture based projection, and then we have a distance based filter. You can open any graph and see what the filter is doing. And let's go to our texture projection. This graph projects a texture on our landscape based on the landscape origins. We can define the texture here. In this case, we are not using a single texture, but rather all of these tiles. Let me make this a bit bigger. So all of these tiles. They are then fed to a texture array, and then we are using that texture array in our filter graph, which assembles all these tiles into a single texture, and then we use that here. Then you need to mention which attribute it's going to target. In our case, it's weight flow, and we mention that same exact attribute here, and then a minimum and maximum value to actually control that filter. Those minimum and maximum values are controlled in our biome asset. Let's go to our desert and isolate our cactus. We define those minimum and maximum values in the parent of our data asset. So under filter option, we have those min and max values. Right now it's taking the value between 0 and 0.2. These are based on the texture's luminance value. So the 0 to 0.2 are close to the black points. And if you see our cactus in the main graph, it's spawning here on those black areas. And if we decrease it or increase it, it will affect it based on that texture. 0 to 1 will bypass it since it covers all the luminance range. There is also control for sun exposure, which is the other texture based filter. It's based on a sun angle. So if we do a lower value, maybe 0.3 or 0.2, let's say, it's like giving your assets a 10. SPF 50 recommended. I don't know which angle this is, but you get the idea. Just any texture, and we are controlling it based on the luminance value. Moving on. With the filters done, next comes recursion and transform, aka the children. Here the child assets are controlled with a transform graph and a limiting global parameter, this max child asset depth. It will tell it how many generation of childrens do you allow. I say more than 2 is not ideal, but who am I to judge? If we have 2, it should take a bit. Another angle maybe. Not every one of them is spawning them, but the smallest one are the one just spawned. And if we lower it to 1, then these will go away. And if you have 0, then only the bigger boulder would stay. So the bigger one is the root point, and the smaller one, that is a child of this one, and which is parent to the smallest ones. You can also use the smaller one as a root point, and it will spawn the ones below it in the level 1 child asset depth. Let's see an example. So our rock has a child asset, and that child has its own transform graph and another child asset. Let's remove it for now. So this graph here transforms the root point that it's parented to. And then if we give it another child, then that child would need its own transform graph that transforms the points from its immediate parent. And if you put another child here, the cycle goes on and on. You can even use a transform graph here so that you can also use this data asset as a child, and it will spawn in the hierarchy. So it's also a parent and a child at the same time. As long as it has a transform graph, it can be used as a child. And how this happens is this child will take the root point of its parent. So let's say this one here, and then it will apply the transform graph. You can open and see what all of this is doing, but basically you select how far you want to go from the parent. Again, you can create your own. I think it has some other interesting ones. It's transformed, so you can do a lot of pretty things with this, like this pattern right here, resetting it back. So what this particular graph actually does is, it takes the root point, it transforms it, and duplicate the points to alter their positions. Then it applies a scale depending on the distance from its original parent. And finally output those points for spawning. And also use the filtering as well. It's the child filtering, not the root point filtering. And if we say like 0.3, yeah, less points for us. And who says this raw cassette can have only one children? You can duplicate this, and instead of this child, we can use some other child. It will spawn 2 of those children, and using this weight control here, you can select which child is given more priority. I see all you parents giving priority to the smaller one, and I'll do the same. Let's put it to 3. And you'll see more of the smaller ones and less of the bigger ones. That's our recursion graph. Next is spawning. It can spawn mesh, a PCG data asset, and an actor. Let's open the desert biome asset. Right now it's spawning a mesh. Let's instead spawn a mannequin. Remove the mesh in case it's spawning right on top. Wrong actor, wrong actor. Oh, we are using a animation blueprint. Let's actually create one ourselves. Maybe a character. Let's give it a skeletal mesh. Can be anything. And let's use that instead. Spawning them here. Let's get rid of the mesh so you can actually see them. And there you have an army of mannequins. Because who doesn't want a fashion show in the desert? And for our assembly, this is where we put our PCG data asset. Let's show you how to create one. We'll bring in a plane. Let me move it up and scale it up to 100. We want to create a level instance. So let's go to where this mesh is and pull in a few of the meshes. After selecting all of them, we'll right click and in level create a level instance. Make sure the pivot is at the lowest point. Let's give it a name, tree assembly, and save it. Find it in the content drawer. There, right click and under asset actions, click this create PCG data asset. That created the data asset that we need here. And we'll remove the mesh and use that in place of assembly. Let me just drag it in the level. Instead of the mesh, we spawn this level instance that created this PCG data asset. If you make any changes to your level asset, then you need to recreate that PCG data asset again. With the spawning done, let's move on to our output. It takes this point data and then outputs them for later use in the runtime graph. Let's find and open that. So here we are using a getPCG component and accessing that data. So in your PCG Biome Core, make sure this is turned on so that we are putting the data out for the runtime generation. And this is our runtime generate graph. If we right click and hit play, like that, around the camera. So let's turn our editor into a runtime source. It's generating those points at runtime. No surprises there. It's also spawning them on some of the biome assets. And with that output data, we have interactions between the biome asset and the runtime assets. Let's take an example. If you notice the cactus here, let's open the biome asset. under the runtime options, making sure that the export points is on. So here we are spawning. We will be using the data from these influence points. The data asset can have an influence on the points, whether it be an add. Did it make a difference? Doesn't seem like it. Let's try it with the boulders. And nothing. Right. So we'll have to refresh it. Unlike the PCG Biome Core, the main core graph, the runtime doesn't refresh that well, so we'll have to do it manually. Let's look for a better spot. And here let's add and refresh. So it added to the density of those runtime assets. We just had to refresh it. So when the influence is set to add grass, then it will increase the density of those points, and when it's set to remove grass, it will remove the density. And this is the default state. We'll have to refresh it every time. But yeah. It also has a influence radius, so which can be adjusted based on how much you want to remove the data from that root asset. So with almost 4 meters of the radius, everything around it is gone. And if we move it to, let's say, 200 and refresh, you can see it being moved. If we do the opposite and add influence, then it will increase the density in that radius. So you can see the ones closest to them are really, really dense. So that's what the influence points data is doing. These biome points take the data from our biome cache, and the runtime data asset will use it. It will help it decide what to spawn in each of the biomes. So in here it's spawning these cube-like things. And if we go to our broadleaf, it's spawning the grass type mesh. And if we move to any other biome, here it's spawning these flat types. And up here in the coniferous, it's spawning these spear type assets. So yeah, different assets based on different biomes. That's what the biome points is doing. The instant points data, this one is sending the target location for the mesh. And next, let me pull up a data asset. And this here, export points or not. If we go to the cactus, you can see if we turn this off, then these points should go away. Don't forget to always refresh the runtime graph. So with the export points turned off, it won't send that point data. And when it's turned on, then the final mesh point sends that data. And the points will start spawning on that mesh. So that's how the PCG Biome Core graph works. You might have noticed by now that we skipped a few things in here. Oh, how dare you! We missed talking about this sky blue data. These all four here. It's all injecting the external data, and we'll cover it in the, which is it? One of these parts later in the series. I think it's the artistic control one. For a quick summary, our biome cache here stores the biome data. This is where the overlap between the biomes are decided, and each of them are given a pretty color depending on their personality. And the council of all of the splines, volumes, and the texture projection shall decide the biome cache. Next, our generators work hard day and night to create those root points, which are then told to find their biome personality and assigned a biome asset. On the side here, all the assets are stored in a root asset table. The points are very weak from constant working day and night. Some dare say they are overworked. Then they are told to take care of their bounds, their rotation, their translation, which biome they belongs to, and what child they have. That's a lot of pressure for those cutesy little points. So they are not given all their parameters. Instead, when we are assigning them, we give them a unique mesh ID. And if we inspect our root asset table, it stores everything about that asset and it has that unique asset ID. That simplifies a lot of things. We don't need to assign all the parameters to each of the points. We only need to give it a unique asset ID. And if we need anything, just give it a asset ID and ask the root asset table for those parameters. So once asset ID is assigned to that point, it only needs to hold that. It's like a VIP list, only the coolest assets can get in. Then there is a priority-based difference operation, and we move on to our filters. After the pitiful points come home from a hard day at work, you tell them which area of the biome house that they belong to. You use different filters like density, position based, and the texture based. So you just give them a map and say, you go here. The poor points. You sound a bit too cruel for my taste. You best stay away from me. After coming home, the points start working on children using a transform graph and recursion, meaning you have generations of children and you control them with a global parameter max child asset depth, and the children also have their own filters, which is usually none, little rascals. Moving on, we finally assign them a mesh or an actor or a assembly. Then we output some of the data for our runtime graph that we later access using a getComponentData node. So that's our main Biome Core graph. Let's take a final look at this map. Quite pretty, but we'll make our own in the next episode. These points work so hard, they deserve a vacation. And unlike you, I am not a cruel man. So I'll give them a long rest. But before we sign off, let me introduce to you the people that make tutorials like these possible. Oh, I must have had too much Drake beer. I can't seem to remember where I put my Patreon link. I am so tired I can't even lift my mug of beer. By the way, now fearless explorer, and someone roll in the music.